All right, so we're starting a new series of videos on explicit chemistry, which is the book for JAMB Chemistry exam. And I'm going to be taking the first topic in that book, which also represent the first topic in the JAMB syllabus. If you check through our old videos, we have actually um, done this topic before in form of question and answer, but now this is the video that would be doing more justice to the requirement of the syllabus as regard this topic. So, for those of you who can find the book, then you can actually join along in this journey. But for others who may not have access to the book, of course, any good chemistry textbook would also have covered this topic adequately. So um, I would first and foremost refer us to the JAM syllabus before I begin, and let's see what the requirement of the JAM syllabus is before we begin. So if you look at the JAM syllabus, which is the very first topic here, you have separation of mixtures and purification of chemical substances. You're expected to know what pure and impure substances are, also um, boiling and melting point, and also elements, compound and mixtures, also chemical and physical changes, and separation processes. And you have these different types of separation processes that we're going to be looking at. And the objective of the syllabus is that you are able to distinguish between pure and impure substances, and also be able to use boiling and melting point as the criteria for purity of chemical substances. You should be able to distinguish between element, compound, and mixture, be able to differentiate between chemical and physical changes, identify the properties of the component of a mixture, specify the principles involved in each separation method, and finally, apply the basic principle of separation processes in everyday life. All right, so we go back to the book that we're using for this preparation, which is explicit chemistry. So we begin by looking at what pure and impure substances are. So here we have um, the very first topic, pure and impure substances. Now, what is a pure substance? Of course, a pure substance would have no impurity. So the absence of impurity in any substance makes it pure, and that is what distinguishes it from an impure substance. In order to test for purity of substance, you use their melting point, their boiling point, and their density. For a pure substance, it must have a precise melting point, a precise boiling point, and a definite density. In other words, for example, if you have pure water, it will have a melting point of 0 degrees Celsius, and it will have a boiling point of 100 degrees Celsius. But if it's an impure substance, it would have a range of melting point. In other words, it will melt over a range of temperature. In other words, it can have a melting point of 0 degrees Celsius to, for example, say 2 degrees Celsius, and a boiling point of, say, 100 degrees Celsius to, let's say, 105 degrees Celsius as a result of the impurity that is present. So having said that, what are elements? Elements are substances which cannot be broken into other simpler units by an ordinary chemical process. So that, in other words, elements are the basic form that a substance can exist in, a chemical substance can exist in. For example, you have copper. You cannot reduce copper below what it is already. Of course, copper can participate in a chemical reaction to form other compounds, but it cannot be reduced any further than what it is already. And of course, we know the periodic table is that table that groups all these, that group all these elements in different categories for easy identification based on their properties. And now let's talk about compound. Compound, on the other hand, are substances which contain two or more elements chemically combined together. So a compound is formed as a result of a chemical change and a new substance with entirely different chemical properties from those of the component element. So for example, in water, you have hydrogen and oxygen undergoing a reaction to form water. So what happens here is that in this reaction, right, in this reaction, um, hydrogen as hydrogen in the water is no longer the same as, oh no, I take that again. So, talking about compounds, compounds are substances which contain two or more elements that are chemically combined together. So, the key word here is the chemical combination. So, a compound is formed as a result of a chemical change and a new substance with entirely different properties from those of the component element. So, for example, in water, which is formed by a reaction between hydrogen and oxygen to form water. So, let's say, for example, in water, so what happens here? The water that is formed, the hydrogen and oxygen will behave differently because they have been chemically combined. So water behave differently from hydrogen or um, oxygen, right? So a new compound formed would have a distinct property different from the individual constituent of the compound. The same applies to limestone, for example, where you have calcium, carbon, and oxygen. In limestone, there is a whole new property that is different from the individual property of calcium, carbon, and oxygen. But then if we go on to look at mixtures, mixtures contain two or more constituents, two or more constituents, and they are joined together by physical method. as against in compound that are joined by chemical method. So in that case, the constituent of a mixture would retain their individual properties or individual identities because they are physically combined. For example, if you have air, which is a mixture of gases such as oxygen, carbon dioxide, and also you have nitrogen. Now, in the mixture that forms air, each of these constituents still retain their individual identity. You can actually test for oxygen in the mixture of air. You can test for CO2. You can also nitrogen still um, retain its individual identity. And that is the same thing you have in seawater, where you have sodium chloride and H2O. So, constituent of mixture can be elements or compound or both. Take for example here, you have a compound, sodium chloride, and another compound, water, forming seawater, which is a mixture because you can take out this constituent and they are not chemically combined. Now, let's talk about chemical and physical changes. So, chemical change is any change that results in the formation of a new chemical substance. So, at the molecular level, chemical change involves making or breaking of bonds between atoms. And when this making or breaking of bond occur, a new substance is formed, and most of the time this reaction might be irreversible in some cases. And as a result of that, a chemical change is said to take place. You have different examples, for example, the rusting of iron, which forms iron oxide. In rusting, you have iron plus oxygen, and that will produce iron 2 oxide, and that will be Fe2O3. And you have this as 4. So that is a chemical change because a new compound has been formed. And the same applies to other examples that are listed here. Now let's go on to look at physical change. In physical change, there is a rearrangement of molecule, but that doesn't affect the internal structure of the compound or the substance. So some examples of physical change are, let's take the second example, magnetizing a compass needle. When you magnetize a compass needle, there will be a realignment of the ion atoms. But that is not a real change within the ion atoms themselves because the realignment is not changing the fundamental nature of the substance in question. The same applies to boiling water. Of course, when you boil water, you are only changing the state of the water from liquid to gas. So this is an example of a physical change. When you dissolve substance in water, for example, sugar in water, that is an example of a physical change. Now, let's take a closer look at change of state, whereby matter changes from one state to the other. For example, a change from solid to liquid and from liquid to gas, or a change from solid directly to gas. So, number one on our list here is melting. So, melting is a change of state from solid to liquid. We have boiling, which is a change of state from liquid to gas. We also have sublimation, which is a change of state from gas to, from solid to gas without first becoming liquid, or from gas back to solid without first becoming liquid. So what has happened in sublimation is that you have actually bypassed the liquid state. So for example, if you have solid at this point and it changes into liquid, and then the liquid changes into gas at this point, and the solid changes directly into gas at this other point. Then this process here is called melting. This is melting at this point. And mind you, this is a reversible process. It is reversible because the liquid can then changes back into solid by the process of freezing. Also, liquid can change to gas when you boil, or by the process called evaporation. When you boil, it undergoes evaporation and the liquid will change into gas. And of course, it's a reversible process also. So meaning that the gas can then change back into liquid. By what process is that? That will be by the process of condensation. By condensation, you can change this back. All right. And also, when you change solid directly to gas, I mentioned that that is sublimation, sublime. Okay, sublimation. And this is also a reversible process. And both cases, it's referred to as sublimation. So you have forward reaction and backward reaction for all of these processes. So having said that, then go on to talk about, let's go on to talk about um, exactly what is the molecular nature of melting and boiling. What exactly is going on when melting and boiling is taking place? So, for melting to occur, you must apply heat. And what does the heating does? The heating actually gives the particles more kinetic energy, and this kinetic energy makes them to move faster and further away from each other, until at some point they have enough energy to overcome the forces that is holding them together. So you have these particles here, and then they begin to move away, they begin to move apart as a result of the gain in kinetic energy. It gets to a point where this this increase in kinetic energy would then make them continue. They will be so far apart that they will no longer remain in that solid state as a result of the increase in kinetic energy of these particles. So that point, the solid is said to have melted. That is when melting takes place. And it is important to know that when melting is taking place, the temperature remains constant because what the particle needs is to gain enough energy, kinetic energy, to pull apart. And if we apply the same logic to boiling, for you to boil, for boiling to take place, you must also apply heat. Apply heat to a liquid. And then when you do that, the particles will also gain more kinetic energy and they will start to move even faster, pushing each other away, just like what we have here. So you have these particles of liquid that are already a bit separated apart, and then they begin to move further apart. Why? Because they've gained kinetic energy. And when that happens, the particles have highest amount of energy that can break the forces of attraction and then they escape as a gas. And this is when boiling starts to take place. And again, I will also mention that this is when boiling is taking place, the temperature also remains constant. And the opposite of what is going on here in melting, like I mentioned, it's a reversible process. So when you melt a solid, you can further, like what when we mentioned here, when you melt a solid, you can further reverse the process, and that will be by the process of freezing. So what exactly, if you apply the your knowledge of kinetic energy to freezing here, so we said for this to occur, melting is as a result of increase in kinetic energy, increase in kinetic energy. So for freezing, that will be as a result of what? A decrease in kinetic energy. When there is a decrease in kinetic energy, the the particles will then begin to come closer again, and then they will become bound by the force of attraction holding them, and then they return back to their solid state. Again, when you have the reverse of evaporation, the process as a result of boiling, what happens here would also be as a result of a decrease in kinetic energy, and the gas particles begin to move closer. So by condensation, a liquid state is attained again. So let us look at what a heating curve looks like. This is very important in your exam. You might be asked to explain what the heating curve looks like. So here, the heating curve is a plot between temperature and time. And when you apply heat to um, a solid, for example, this is going to be moving upward. So here, the temperature is going up. That's what you have here. And of course, over a period of time that goes like this on the x-axis. So now there are important points on this curve. You will notice the x and the y, and you will notice that at this point the temperature is constant. The temperature is constant. We'll come back to that. But notice that if you increase the temperature, then the solid at this point would begin to of course it is still at a it is the substance here is still is in the solid state, but as soon as the temperature continues to increase, it gets to a point where the temperature remains constant, but the particles would have gained enough kinetic energy, right, and they begin to pull apart from one another. And at this point, the temperature remains constant. This is when melting is taking place. So X on this curve represent melting. That's what you have here. X is melting. And then it is important to know that A is a solid state. So what is happening here is still a solid state until it gets to B, when melting starts to take place. And when melting is taking place, you will agree that you will still have solid and a little bit of liquid. So B would be the solid when the solid is melting, and it is a mixture of solid and liquid. So you can then see that once the liquid melts, you have and you continue to increase the temperature, you have this point C, which will then be totally liquid, because as you increase the temperature, other particles, I mean the kinetic energy increase, will continue to pull the particles apart. So C is a liquid state, completely liquid at this point. Then you get to another point when you continue to increase the temperature. I mean, you continue to eat, but the temperature is not increasing. And the liquid then will begin to evaporate. You have liquid and you have combination of liquid and gas at this point, which is D. That is evaporation taking place here as a result of boiling. So this point Y represent boiling, and D is a mixture of both liquid and gas. It is important to be able to identify all these points on a heating curve. And finally, we have the point E, which will be as a result of increase in temperature, the temperature is now getting higher than the boiling point. Then what you have here will be completely gaseous state, and that is the point E, completely gaseous state. So I hope that is clear. Then let us now look at the opposite of this curve that we have talked about, the cooling curve. So now you will agree that the logic is just to flip the logic of the heating curve. So now the cooling curve will be the temperature will be decreasing from high temperature to low temperature. That is cooling, right? And then over a period of time. And that is what you have here. So if you begin to cool, meaning that we're going to be starting with the gaseous state, which is, so the entire axis here would be gas. That's A. That's what A represents. The gas is actually, you are reducing the temperature, then the gas continue to, the particles of the gas then will begin to lose their kinetic energy, and they begin to move slower and moving closer into each other. And it gets to a point where the the um, the temperature remains constant, and the gas then condense and become a liquid. So that's this point you have here, point Y representing the boiling point, which is actually an interface between um, the gaseous phase and the liquid phase. All right. And then if you, so B will be a mixture of both gas and liquid. Then as the temperature continues to reduce, you have the liquid remaining alone at this point. So you will have a pure amount of liquid here. This is totally a liquid state at point C. And then you get to a point again where the temperature remains constant over time. But what is going on here, you will be having a combination of liquid and solid, a mixture of liquid and solid at this point D. And that will coincide with X, which represents the melting point. And finally, you get to a point E where you have only the solid phase as you continue to reduce the temperature. So that is how to describe the cooling curve and the heating curve. Now, to recap what we mentioned about purity of substances. Purity of a substance can be easily determined by testing its boiling and melting point. Like I mentioned earlier, this is because pure substances have sharp boiling point and melting point, while those of impure substances, as a result of the impurity, they would have range of boiling and melting point. So that is the end of the first part of this topic. Now let us go to the concluding part of this topic, which is separation processes. Now you should understand that because mixtures, the particles of mixtures still retain their individual identities and they are not um, physically, they are not chemically combined. They can be separated. But in separation process, you must take advantage of the individual property of the mixture. For example, their sizes, their solubility, their rate of diffusion, their rate of movement over adsorbent medium, or also sublimation or other physical properties. For example, magnetic property, all of these can be used as a basis for separation of mixtures. So let us look at different methods. For example, a method that involves difference in sizes. For example, you have one mixture having this kind of particles and it's mixed in fine particles. Let's say, so you have, let's say, powder and stone. As a result of the difference in sizes, of course, you can pass this through a sieve and the, the finer particles will escape through the pores while the bigger particles will be left behind. It is important to understand how the different methods or the different um, principles of separation applies as a result of the differences in the properties of the constituent of the mixture. Okay, so let's take another example, a method that involves differences in solubility. Of course, you can filter, you can sediment, you can decant as a result of these differences. But let's first and foremost start by explaining what a solution is. If you have a solution, what exactly is it? A solution equals solute. Solute is what you are dissolving plus solvent. the medium that is dissolving what you are dissolving. I hope that makes sense. And what these two forms, or what these two form, sorry, will then become the solution. So, because um, in mixtures, this reaction is physical reaction. It's a physical reaction. The formation of this solution is a physical reaction. Then you can still separate the constituent. You can either want to take out your solvent or want to take out your solute from this combination that has formed the solution. So, for example, filtration can be used to separate an insoluble solid from a liquid. So you have the solid, for example, is your solute, and you have your liquid as the solvent. You may want to take out this solid from this liquid. That you can then use the method of filtration. So for example, you want to take out a small scale. You want to take out precipitated salt, that will be your solute, in liquid, let's say water. You can filter. What does this filter look like? Let's go to this image. So we have explained the concept of solute and solvent. We have explained the concept of solute and solvent to form a solution. So here you have your solute, you have your solvent, which is the water, and this will form the solution of salt water. Now, how can you remove the solute from the solvent? We mentioned that you can use um, the method of filtration. So what does this filter looks like? I'm going to show, for example, this is a filtration process. You all have this in your chemistry textbook. So if you want to filter seawater, you can have a glass rod and you have a folded filter paper. And then by the time you begin to pour this seawater into the filter paper, you can separate out the solvent, and the solute, which is the salt, will remain in the filter paper as a residue. So you have your sand or your mud or your salt, and the clear solvent will be called your filtrate or your clear seawater. So this is a typical example of what you need for filtration. And then we go back to look at another method: sedimentation and decantation. Of course, if you have a solute in a solvent that is, for example, you have a solute that is not dissolved in the solvent, then you can actually decant. Decant is just the process of pouring out. So you have this as your beaker, you have, let's say, sand in water, sand plus water. By the time you begin to pour off the water, you will be left with the sand. So you'll be pouring off the water. Of course, this process is called decantation. and also the process whereby the water, the sand settles at the bottom is called sedimentation. Now, this sedimentation and decantation can be aided in the laboratory, particularly when you you put this mixture in a centrifuge. The centrifuge will be spinning at high speed, and that aid the particles to settle faster. Again, let's look at what that looks like. In decantation, you have mixture of solid and liquid. The heavier solid is allowed to settle to the bottom. The liquid poured off while the solid remains. And this process is decantation. And what has settled at the bottom is the sediment. Again, let's go on to talk about another method of separation. This time around, we want to look at precipitation. Okay, now I come back here. Let me see if I have a note on precipitation, which I doubt. Okay, now I go back to the textbook. So in precipitation, you have mixtures of ions. So that's a giveaway actually in the exam. When you have um, mixture of ion and then you are using um, one of the components is escaping out of the mixture or leaving the other component behind in the mixture. That would be an example of sedimentation. And usually it could be as a result of, this can be aided by certain solution. Certain solution can actually promote the process of precipitation. So for example, addition of hydrochloric acid solution containing silver ion and copper 2 ion will precipitate silver ion as silver chloride, and then that will leave the copper 2 ion in the solution. So that precipitation is usually the separation of ions. That's what that's the key point to note here. Separation of ions. Separation of ions. As a result of what property are we using here? Solubility. Let's go back here. Let us not forget. We must not forget the method. Solubility. So you have filtration, you have sedimentation and decantation. You also have precipitation based on difference in solubility, but in this case, you're dealing with difference in solubility of ions. Let's go on to the next one, still on solubility. You have crystallization. When a saturated solution, which is a mixture in solvent, cools, the crystals of the solute separate out from the solution. So, as a result of cooling, crystals are separated from the solution, and such crystals can be filtered off or the liquid decanted to get the crystals. That is crystallization. And when you introduce the term fractional, in fractional crystallization, you imply that you have two or more of this solid. So in fractional, you have group of this solid that you want to separate. What about the use of separating funnel? We mentioned that already, and that can be okay. No, we talked about filter paper. So, but there is also a separating funnel that can be used to separate two or more immiscible liquids. So when you have, for example, a mixture of water and kerosene that do not actually mix together, they can be separated by the use of separating funnel. Now, let's look at a different method that involves differences in boiling point. Under that, we have three key separation processes: evaporation, distillation, and fractional distillation. Of course, you know that in evaporation, you are changing state from liquid to, to gas, right? You're changing from liquid to gas. Now, you can apply that to separate mixtures, whereby, let me give you what that looks like. So here, I'll find an example of evaporation. So you can use evaporation to separate dissolved solid from a liquid. So you have the solvent, which is the liquid, that is lost into the surrounding. So remember, when you have your solute plus your solvent, right, forming your solution. Oh, sorry. Oh no. I take this here and then I come back here. Equals solution. Now, you can actually remove this solvent by evaporating, by the process of evaporation. When you apply heat and have this mixture in an evaporating dish, the water would escape and that will leave behind only the solid. For example, a mixture of salt and water. When the water evaporates, you will be left with the salt only. And that is as a result of differences in boiling point. The water has a different boiling point. The liquid has a different boiling point. Again, we have a method called distillation and fractional distillation. And all these three are based on differences in boiling point. Differences in boiling point. Okay, I go down to what fractional distillation looks like. Now, talking about distillation, it's a process of boiling a liquid until it forms vapor and condense, then collecting the liquid. So the liquid collected is the distillate. So, for example, we have in the laboratory we have what is called the Liebig condenser that cools the vapor back into liquid. And the purpose of distillation is separation of mixtures of two liquids. All right. So you have two liquids being separated as a result of distillation. Now, this is possible if the two substances have different boiling points. So the substance with the lower boiling point turns to gas and is collected, while the other substance with the higher boiling point remains as a liquid in the flask. So for example, you have your condenser here. This is the Liebig condenser, and it has a cooling out portion and the part that water, where cooling water goes in, or water that cools the condenser goes in from here, and water, I mean, hot water comes out from here, like vapor. So the cooling water comes out here and it goes in from this point. So you have your distillation flask, you have your salt water, and you have mixture of two liquids. Now you apply heat what happens as the vapor continues to pass through this? You have your pure distillate that would that will be cooled down again here. So it will become a gas at this while it's passing through this phase, then comes out here as distillate. And that is distillation. So when you apply that to fractional distillation, you'll be dealing with liquid, more immiscible, more liquids, right, with different boiling point. And that is an example of that would be petroleum, or the separation of the purification of crude oil, where you have different components and they are separated out by fractional distillation. Okay, before we go on to the last one, you have method that involve sublimation. And what happens in sublimation, for example, if you have a compound that can sublime, that can change directly from solid to gas, and you have another compound, a mixture of this, you can take advantage of the process of sublimation. So if you have iodine, for example, and ammonium chloride, iodine are known to sublime. So the mixture containing such can be separated by heating and collecting the sublimate on a cold surface above the heated mixture. So when you have a mixture of iron filings, for example, and sulfur, you can separate them out by introducing a magnet that will take out the iron filings. And this method is actually used in the industry to separate impurities from tin ore, for example. So we have another method that involves differences in rate of diffusion. So when you have gaseous mixtures that can be separated by putting the mixture into a porous pot. So the component with the smaller density will diffuse out first, right? And that will leave behind the component with the higher density. So, for example, you have nitrogen and oxygen. They can be prepared from air, which is a mixture, by, they can be separated by this method, taking advantage of their diffusion rate. And finally, method that involves differences in rate of movement over adsorbent medium. I will show you an image for that. So what exactly is an adsorbent medium, and how can this be used to separate mixtures? A popular method is chromatography. So chromatography is a method that is used to separate various substances in a mixture of dye or ink. All right, now substances of the mixture will differ in how much they stick to things. That's viscosity, for example, how much they stick to each other and to other substances. Some of the substances of the ink will stick more tightly to paper fibers. They will spend less time in the water as it moves along the paper fibers, and they would not travel very far. Other components of the ink will stick less tightly to the paper fibers, and they will spend more time in the water as it moves along the paper fiber, and they will travel further through the paper. Now, this is quite simple. If you are separating colored compound, you can take advantage of their movement, differences in movement on this adsorbent paper. And because of their color, they can be visualized and you can now know. For example, you have oil, for example. Let's say you have olive oil, you have palm oil, you have other kind of dye or ink. Mixture of those, they can actually move at different rates over this adsorbent medium. And in some cases, some of these adsorbent medium are calibrated. So you can tell as a result of the level that the dye is on the adsorbent medium. You can actually measure and know that okay, this is this will be let's say chlorophyll because it is standardized. Okay, chlorophyll will always have a particular number on the chromatography paper, something like that. So let's go back to the book. I think on this note, we have come to the end of our discussion on the first chapter in chemistry. I hope this topic has been helpful for you and for your exam preparation. Um, don't forget to like this channel if you have not done so, share, and let me get your comment in the comment section if there are other areas you want me to clarify. In the next video, I would I'll take some questions and answers in this book, which are from the past questions. We'll take some questions and explain their answers. And when we do so, we will then move on to, we have a lot of questions to look at. We will then move on to the next chapter, which is the next topic in the syllabus, chemical combination, which is all about stoichiometry, calculations in chemistry. So, thank you for joining me today. I hope I'll see you in the next video. Bye.